We have done so far, I would say 99% of the real content of Java 2. Okay, what we're missing is really not important. GUI is not really part of Java 2, it's like optional, and trees and all that is really optional. The professor didn't even cover it, so I'm going to cover a little bit of that so that you have an idea. Okay, in programming languages, we have the notion of variables, right? Single variables, what's an integer, a double, etc., right? Now, when we start storing collection of variables, things become more complicated. And we learn about arrays, bidimensional arrays. The objects itself looks like a structure, right? You can have different types of variables inside, correct? All of those are called data structures. So linked list is yet another data structure. A stack is a data structure. Queues are yet another data structure, okay? Pretty much what is a data structure? A structure that allows you to store data, no more than that. Now, there is a class formally called data structures in computer science. It's one of the toughest class, and the best professor to teach that class is Mark Weiss. He's the one that teaches that class. That class is really, really useful and really nice. Sorry?
You haven't teach anymore?
He teaches every now and then. I don't know if he's teaching in fall though, but he teaches every now and then. I think he and Pelly teach that class. I want to teach that class, but normally my schedule doesn't work for that class. That's a very beautiful class. It's like the Bible of computer science. Really tough. If you think programming 2 is tough, that class is 3 times tougher. But very beautiful.
Tougher than programming?
Way tougher than programming. Programming 3 is a cake next to it. It's called data structures. Data structures. But if you want to get a good, decent job in programming, you've got to know that very well. Okay? So, in data structures, the professor normally starts with linked lists. Okay? And linked list is normally the weak point for everybody, just because, like I told you, most professors like teaching linked lists like import Java util linked list. Linked list L equal new linked list. And they start calling the library methods, right? They don't really implement what's a node, how you connect, and all that. They don't do that, right? That doesn't happen. So you guys learn that, so that's good for you. So when you want to take those classes, you will be prepared. So besides linked list, some of you were asking me last class, Professor, when you create a linked list, you create a notion of a node where you have data and you have next to point to the next item, right? Now, remember when we were trying to delete a node or find a node and we had to go look ahead and we were saying get next, remember? So you can also create a node with 3 parts. We'll share your data. This guy is obviously next. And you have another guy to indicate previous. It's not really hard.
And they say we couldn't go back. Those are already going
You cannot go back in the kind of linked list that I taught you, which is singly linked list. This is called doubly linked list. So a doubly linked list is no more than a singly linked list where each node now has previous and next. No more.
That's a double.
That's a doubly. It's called doubly.
Doubling.
Doubly. Yeah, it's like double, but you put a Y.
Okay.
Like single, but you put a Y. Singly.
Singly and doubly.
Yeah. I know. Yeah. Maybe the guy that wrote this code was wearing pink or something. Anyway. So, you had these things, right? Obviously, remember when we had singly linked list? The last node that we call tail, for example, right? What was his next pointing to? No. If I have a double linked list, a double linked list is going to look like that, right? This guy points here, this guy points here, right?
Right.
This guy points here, and this guy points here, right?
Right.
This guy's next is going to point to null, obviously, just like before. But this guy has a previous to, right? What should it point?
No.
So the head points to null.
But also, can you connect the null with the other one?
Same as in the singly linked list. Remember when you asked me, can I connect the last node to the beginning? Then you create a circular singly linked list. If I connect this guy here and I connect this guy here, I create a circular doubly linked list. That's something you can do too. Okay? Now, remember I told you you can do this, and then you create a doubly linked list. You can play with nodes and do crazy things. I can create a node and say data. Okay? And now, I want to point down, left and right. So, visually, I'm going to create a node and connect each node like that. And this guy can connect left and right. So you're creating like that. Here's your piece of data in the middle, right? Another node, this guy opens into. Another node, this guy opens into. He doesn't have to have a child here. He can have, each node is called a child. Each node that comes from there is, so this is the parent, these are the children. If you see like that, could be the grandpa, the parent, and the children. Okay? Now, this is considered a tree. And that's why they think computer scientists are smoking weird stuff, because they say a tree normally looks like that, right? Here I have the root, and here I have the leaves, right? Here is the other way around. Since we smoke weird stuff, at the top we have the root, and at the bottom we have the leaves. that's the name of it. The concept is like that. The root is the first element that from where everything starts, and the leaves are those nodes which do not have any more children. Like this node cannot be considered a leaf because he has one child. But this guy doesn't have any more children. So this guy is a leaf.
So what is the other one called? Branches.
Which one?
So like the
It's
second
called branches actually. Branches. Every time you open it's a branch. Sorry?
No, yeah, I guess you answered the question. The branches.
Yeah. Now,
So an inheritance of a node,
sorry?
that's part of the inheritance of a node?
We're not talking about inheritance here.
No, what I'm saying, like, that's, I guess, inheritance.
It's similar, like when I represent the inheritance, very similar. Now, you have a question?
Yes, how does the side of the node break down to two? It can be that. Like you have
Every node will have a piece of data in data. Instead of having previous and next, we'll have left and right.
but the nodes. You have left to right, left, and then your previous, and then your next.
It's different because remember, when you talk about previous and next, you're talking everything horizontal, sequential. But when you start saying left and right, you're going down. Got it?
Yeah.
So if you start connecting every node with left and right, you're going down. You're not going horizontal anymore.
The top, the top view.
The top?
There would be the top view, not going up there.
Yes, the top is the root.
How do you do it?
No, he means like if you were going up, like,
You strictly
like a
go
tree, like a regular.
Okay, you're strictly going down. Exactly, that's what I'm saying. Our trees in computer science are always like this, not like the ones you're used in the streets. Okay? Now, this is the very simplest type of tree. This is called a binary tree. Why binary? Because every node has two children. Binary comes from two. Is this useful? Extremely useful, especially for search. Imagine I want to store numbers. Imagine how I store numbers in a linked list, for example. Even if my linked list is sorted, and I have 5, 10, say 15, 23, and 47. And I'm looking for element 23. And I'm looking for element 23. I have to look here, 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 right? What's the worst case scenario? That I look all over, right? And I make n comparisons, right? N meaning the number of nodes, right? That is called time complexity of big of n. You do n comparisons.
That looks what?
That is called big of n. That's the notation we use to indicate the time complexity, how much time it takes me to find an element. Big of n. Why? Because I will need to do in the worst case n comparisons to find the element. Meaning that if I'm looking for the last element, I'll have to check one by one, even if it's sorted. Got it? But in a tree, I can always play like this. I put a number, somebody tells me store 5. Say, I will organize this in a different way. So I'll put 19 here. I'll put here on my left whatever is smaller than me, say 10. Here on my left, whatever is smaller than me, 5. On my right, whatever is bigger than me, say 23. And here, say 41. Got it? Now, why is it faster? If somebody tells me, look for number 23, I start on the root. Then I say, is it bigger or smaller? Bigger than this guy. So I don't have to check on this side anymore. This side is omitted. Now just move here and look here. Is it what I'm looking for? Yes. And if it's not here, and it has more stuff here, imagine it has a bunch of stuff here, and it's bigger than this, I ignore all this. So every time I'm removing half, this has a time complexity of big log n. If you apply logarithm of n, it's smaller than n, right? Logarithm of 100 in base 10 is 2. But 2 is smaller than 100, right? You understand what I'm saying? Doing a little bit of math. I know you don't like math, but doing a little bit. Right? So this is much faster. Okay? That's why we use binary tree. When you do searches in your phone, for example, for contacts, it's a binary tree. Because you're looking for a number. Do you remember that yourself when you type a letter, like M, and it starts showing all the people from M down, so it ignores everything else, right? Yes.
So like like in an operating system, the folders and all that, is that you?
You would use something even better than this, which is a B tree. It's much more complex.
A V?
B tree, like
Big tree.
B, like letter B. And the B trees look like that. They are much more complex. You can have a binary tree, or you can have stuff like that, and then this guy can be connected. So you have different levels per node. They become much more complex. It's crazy stuff. Good stuff though. Okay? It's very complex. Very, very, very complex. But it's very powerful too. How do you think Google does all the searches? How do you think Google takes so little to give you an answer when you search for something?
Something like that.
All their pages are indexed with trees. How do you think databases work? Databases work with trees. That's why searches can be done faster. Imagine if they were all sequential. Imagine if you want to search for a website sequentially, Google were like that. It would take forever to find a page, right?
No matter how fast.
It has to be taking false positives all the time, like half, right? So the idea is, and that's why I put so much effort. If you realize I have put so much effort in linked lists, and I drew the bubbles, I brought different colors for that, right? Because I wanted you to understand how a node works. And after I told you, really, forget about linked lists. Let's understand just one node, remember?
Yeah.
Because once you master how one node works, you understood linked lists much easier. Now, if you are to take data structures or any other class with any professor, and he starts doing trees, you will understand why a node connects to other nodes. And you will understand how one is referenced to the next and to the previous, or to the left and to the right. You understand what I'm saying? So all of that is very, very useful, and it pays off a lot. Okay? I took a class, I told you, Advanced Java, like a year ago, and one of the students there, he took that class, and then he got a scholarship, a presidential scholarship with everything paid in a university in Illinois. The guy was even he didn't even have papers, but he won a math competition and he got a scholarship there with everything paid. And that kid's very smart. He went there, and his first staff class was data structures. And he was so grateful because he knew linked lists, and he could understand trees and everything like nothing. Because understanding the concept of how a node connects to other nodes, why do we have next? Why do we have previous? How do I change the reference from one to other? When we want to remove, we want to skip, remember? Or we want to add sorted. Which connection should I do first? This guy or this guy, remember? And we discussed that. All of that is really powerful to understand other concepts. And if you don't draw them, it's very hard. Remember when I told you one or two? Imagine I would have drawn. Would you have understood that? Most likely not. It's very complicated, right? So that's key, guys. So that's why I don't have time to do this, because this is part of another class, more advanced class, like data structures. But I at least give you the idea of how it works. Now, there is another data structure that is very famous and very powerful called maps. Okay, a map or a hash set, there are different map, hash sets. But the way they work is with a key value. All of you are familiar with a database. All of you have used a database, right? So, say the normal key values that you are used to is, for example, their link has their link variable. She has an ID, right? And a student ID. So the idea of a tree, of a hash set or a map, is to have key value pairs. Key value pairs. So, like a table. So you can have her Panther ID here, and here her name. This would be the key. This would be the value. Why do we call it key and why we call it value? Because the key is meant to be unique, and the value can be anything. For example, I can have, say Panther ID, just put a number, 179, and say here Darlene Vanderwall. Here 181, Charles, whatever. There could be another one, 192, also called Darlene Vanderwall. But this Darlene is different from this Darlene because they have different IDs, different keys, right? So that's the idea of having a map. In a map, you can store a collection of key value pairs. Now, is that the only way to play? No, you can also create for one key multiple values. How could I do that? When could that be useful? When I want a group or an organize data. For example, I want to organize data in my students here by their nationalities. So I can say here, for example, my key, and here my values. So my key can be, for example, nationality, say Cuban, majority of people, right? Say values, I can put all names here. Say Carlos,
Yeah.
Coma, say Osmani, right? Say Alberto, I don't know if you're Cuban, just make
Ecuador,
it.
yeah.
You are?
Ecuador.
Ecuador, okay. So you can put, I will take you out. Say Ecuador here. I can put Ecuador here, Alberto. I mean, maybe he's the only one from Ecuador, but that's fine. He can have one or more values, right? Then say USA, I can put a bunch of names, right? So if somebody tells me, can you tell me if all the people that are Cuban, for example, I can just look up the key, and from there I get all the values. Got it? Instead of having them all disorganized and being asking one by one, are you Cuban, are you Cuban, are you Cuban, are you Cuban? Got me? So this allows me to organize data and make searches faster. Yes?
So like you would store, like, for example, Cuban, all the values, and the map would take care of that, or you
The
would
map
have
will take
something
care of that. The map will take care of that. The map will store this key, and for this key, it knows that all these values are corresponding to this key.
Now, if you find just the value, can you, does it reference the key?
No, because I could have Ecuador Alberto,
Oh,
and
that's
I
right,
could
okay.
have France Alberto, for example, right? So it's not really unique. Remember, your values, there's no guarantee it's unique. This is unique. Got it?
Yep.
Clear?
Yeah.
So this is a map. We have seen already array list, linked list, and all that. So you have a very good idea of how things work, right? Okay, that's about it. We're going to go over the last chapter. When are you presenting your project in this class, right?
Wednesday.
Not on Monday, on Wednesday.
The 18th. There's a
Okay, we're actually in good shape. Some of you could present on Monday if you want. Does any of you want to present on Monday for extra points?
I'll let you know.
How many extra points?
You want like 10 points?
How many extra,
10, 15 points?
how many extra?
Yeah, how many?
20 points? 15.
I don't know, let's say 30 points or something.
How many?
Three?
Three? For everybody, right?
For everybody that answers correctly, right?
Right, right. Plus.
Okay, yeah, plus whatever else you do, yeah, actually, no, that's true, plus whatever else you have. So this is something, I'm gonna start with GUI, I have very little time now, so I'm gonna start with a very lame way of doing GUI, okay?